Hi, we're Team A7, and we designed the A7 Phoenix. I'm Andrew Sarnowski.
I'm Paris Sanadi.
I'm Mike Vreeland.
And I'm Adam Thomason.
I'm Taewan Soo.
So our mission is to design a new close air support replacement for the A-10 Thunderbolt II that can provide continuous airborne armed overwatch and close air support for ground forces, as well as support for other aircraft operating in the region.
Our project stakeholders are United States Air Force, U.S. government, taxpayers, the manufacturer, society, and suppliers. Based on what they needed and required us to have for a plane, we came up with some requirements such as 2 people cockpit, maximum airspeed of 300 knots true airspeed to evade ground attacks if necessary, and maximum design load up a factor of 8G in case it needs to maneuver aggressively during the combat.
So there are several potential risks we had to take into account before we could really begin to formulate our concepts. A couple of these potential risks that we had to look into were mechanical failure and enemy fire. Now, these two risks in general kind of go hand in hand because the biggest risk of mechanical failure is due to enemy fire, where a shell can hit the engine or hit the wing and could cause a catastrophic failure of the aircraft. Another couple risks that we took into account is the varying weather that an A-10 would have to deal with due to the fact that the A-10 is used around the world, not just in the Middle East, for example. It could be used in Korea, it could be used in Europe. All these different regions have different weather patterns, and you have to take into account these capabilities, otherwise you could, in fact, lose the aircraft.
For the design process of the sizing, range, and endurance of our aircraft, we started from the requirements we need to satisfy. After that, we made several assumptions in order to get the unknown values that we do not have with the basic requirements. Here are some of the assumptions we made. The first one is the slope condition, which is the steady level and unaccelerated flight condition. And the second one is the payload and a crew weight as 14,800 pounds. And the third one as we use the airfoil data of the NACA 23013. For the calculation, we used the loop calculation for the sizing, and we used the equation calculation for the range and endurance. We actually changed some different configuration until we could get the requirements that our customer needs.
For the engine selection of our aircraft, we first looked at the A-10 Thunderbolt II and the engine configuration and engine type on that aircraft. We considered that after looking at this aircraft compared to other aircraft and engine types and configurations, that this configuration and type of engine was best suited for our aircraft, considering we have an aircraft that is very similar in weight to the A-10 and that the A-10 performs a similar role as our aircraft would perform. The engine placement in particular offers a few advantages. It offers a ease of maintenance on the aircraft and increases our payload capabilities, and also performs to protect the engine better from ground fire. In figuring out the tail configuration for our aircraft, we first looked at the A-10 Thunderbolt II for a little inspiration. We saw that there's much to be improved on the A-10's dual tail design. And we looked at a whole host of tail configurations on many different types of aircraft and looked at the advantages and disadvantages of them. In the end, we picked a T-tail style configuration because of a few different things. The first was because it offers a clean airflow over the elevator of the aircraft, given our engines are just ahead of the tail, and the engine exhaust does not interfere with the control surfaces on the tail. We also picked it for its good pitch characteristics, especially considering our aircraft is going to be operating at low altitudes, and also for its stall characteristics.
For the A7 Phoenix, we looked through multiple configurations for the wing, and we ended up deciding to go with a rectangular wing platform because it's simple and has great low altitude performance. A rectangular wing platform also means that we have many constant parts from root to tip, which means it's easily manufactured and easy maintenance as well in the field. We decided to go with a low aspect ratio for this aircraft due to the characteristics of high roll rate as well as fantastic handling capabilities with that low aspect ratio. We decided to go with the 23013 airfoil due to its great lift coefficient, as well as it's not affected by roughness on the surface of the airfoil very much, which means that in moderate icing conditions and rain, any sort of weather, we can really not be afraid of that with this airfoil. Lastly, one of the negative things about the NACA 23013 airfoil is its poor stall characteristics. It has a rather abrupt break, which isn't that great for the pilot. To mitigate this, we have a slight twist from the root of our wing to the tip of our wing, which means that the tip of our wing is at a slightly lower angle of attack, and therefore you still have aileron control into the stall, which allows for better recovery from the stall.
We took the remaining data from the slides that were just presented to you, and we formulated a final concept design, as you can see above me here. The final concept is the derivation of our best choices based on the recommendations and needs of our client.
The lessons that we learned for this in this project are two, general and technical. The general lessons were we realized that it's better to meet in person rather than just working together in Google Doc, as well as we realized how we can make the document look more professional, like publishing our MATLAB code instead of just copying it there. And we realized also that the milestones are important, since we have to do the project over some period of time, and it's better to do it in little by little throughout our time period than to rush it at the end. The technical lessons that we learned were how to select the best design between all the designs that exist. So we came up with tables for pros and cons and all the advantages and disadvantages of both all the designs that we thought for, and then we selected the one that would fit more for our project.